Hello, in this session we will be discussing one of the very important topic that is called as iron carbon diagram. Now before going to iron carbon diagram, so one more concept that should be known is phase diagram. Now what is phase diagram? So phase diagram is a graphical representation, so where we can look at what are the changes that occurs in the phases with respect to concentration and temperature. Now suppose if you want to form an alloy, so where two metals are heated, so and then they are mixed together, and during the process of solidification we get an alloy. Now this during the process of solidification where temperature drops, concentration of one in another goes on changing. So that phase change should be studied. So at what concentration and at what temperature, what is the phase that is existing? So what is the phase that is existing? So that study of this change in phases with respect to concentration and temperature, that is called as phase diagram. Now iron carbon diagram is under the phase diagram. We study this iron carbon diagram. It is in other way, it is a type of phase diagram. Now phase diagram, it can be a study of any two different alloys. Any two different alloys if you can take, and you can study the phase changes, how it occurs with respect to concentration and temperature. So whereas this we are studying at a particular topic or particular heading called as iron carbon diagram. Now what is the necessity? Now if you take any product, majority of cases material used is iron. Majority of product that is manufactured, material is used iron. Now iron, we can have different forms of iron. So just to name: steel, cast iron, alloy steel, tool steel. So how we get this variation, or how we get this different types of, that is iron. So this is what the changes occurs. Now all these types of that is iron, what we get is variation in carbon content. So when carbon is added into iron, so as the percentage of carbon varies, we get different forms of iron. Now hence it is very much important to know the changes that occurs when carbon content is added, so in different percentage with respect to temperature. So with respect to temperature, so that is carbon is induced into iron. So it may be in solid form, liquid form, or gaseous form. So carbon is induced. So whatever may be the form, so it has to be heated to a temperature and then it has to be induced into iron. So hence the changes that occurs with respect to temperature and your, that is, composition of carbon, that is what iron carbon diagram. So from this iron carbon diagram, so we can study the changes that occurs in iron with variation in temperature and percentage of carbon content, that is what iron carbon diagram. Now how we get the iron carbon diagram is that we can plot taking carbon, percentage of carbon on x-axis, and whereas temperature on y-axis. Percentage of carbon, that is on x-axis, temperature which will be in degree centigrade on y-axis. So this is the iron carbon diagram. So here how to draw is, so percentage, so you can see the variation. It starts from 0 and it is from maximum is 6.67%. Similarly from 0 it goes to a maximum temperature of 1538. So taking this variation we can draw the iron carbon diagram. Now once we draw the iron carbon diagram, so very important is to analyze or study the iron carbon diagram. Analyze and study the iron carbon diagram. So which are the different interstitial forms of iron that can exist? What is interstitial? Interstitial is one where already we have seen in the previous sessions, so where the impurity atom occupies the interstitial space in the crystal structure, whatever may be the type of crystal structure. The interstitial atom here, carbon is the interstitial atom which occupies the structure of iron, so in the interstitial space. So what are different interstitial forms of iron we can study. So before that, what are different points that we have to study in this iron carbon diagram. Now here basically iron we can have two types. So one is steel, under steel we can have different types of steel, and one is cast iron. So you can see this x-axis percentage of carbon. So that is starts from 0. If the carbon content is from 0 to that is 2.3%, so then it is called as steel. Then that particular type of iron is called steel. If it is between from 2.4% to 6.67%, then it is called cast iron. Now here once again we can have if it is from 0 to around 1.6%, it is hypo-eutectoid steel. From that to 2.7%, it is hyper-eutectoid steel. Similarly, from this point to this point, it is up to 4.3% carbon content, it is called as hypo-eutectic cast iron. From 4.3 to 6.67%, it is hypo-eutectic carbon, that is cast iron. So steel and cast iron. Similarly, on the y-axis is temperature. So initially it will be 0. So the carbon, that is iron with 0% of that is carbon content and 0 degree temperature, that is the purest form of iron. So it starts from this point. So 0% of carbon content at 0 degree centigrade, what we get, that is the purest form of iron. Similarly, maximum 6.6% of carbon content, maximum 6.6% of carbon content, and a temperature of 1475 degrees centigrade, that is called as cementite. That is called as cementite. It is represented as Fe3, cementite Fe3. So this is the hardest type of iron. So this is the pure iron, 0 degree centigrade and 0 degree and 0%. So maximum 6.6% of carbon content and temperature of 1475, that is called a cementite type of iron. That is the hardest type of iron. Next, you can see these are the different forms. So the line A, B, E, C is called as a liquidus line. So A, B, E, C is the liquidus line. So this curve, what we can see, that is called as liquidus line. So liquidus line is the line or the mark up to which the material will be in liquid state and or the point from which solidification starts. So above this portion it will be liquid. You can see this here, liquid. So from here solidification starts where phase change occurs from liquid to solid. Now this curve, so BE is called as the liquidus, it is a liquidus line. It is the point where austenite begins to solidify. So austenite is the stable iron state. Austenite is a stable iron state. So as the temperature drops, it becomes unstable and changes into different allotropic forms of iron. So this region, so here this point, that is this curve, so liquidus line is the austenite begin to solidify. So up to what? Up to a temperature of 4.3% of carbon content and a temperature of that is 1475 degrees centigrade. So that is the point where austenite begins to solidify, changes to other forms. Then similarly, if you look at this curve E to C, so it is also a liquidus line. So above which the iron will be liquid state. So this is the cementite begin to solidify. That is from 4.3% of carbon content up to 6.67% of carbon content at a temperature of 1475 degrees centigrade. So from this point, so austenite, that is it will be in cementite. Cementite begins to solidify. That is where up to this portion it is austenite. From this portion, that is from 4.3% it is cementite. So where it cementite begin to solidify, that is iron which is in cementite form, it begins to solidify. Then you can look at this region, that is this is the delta region. So from here to this point, this is delta. So this delta plus, so delta is nothing but other which are the different phases that come in iron carbon diagram. So then this region, so this point is called as peritectic point, PP. So peritectic temperature, PT is peritectic temperature, that is 1475 degrees centigrade. And then this is the region that is alpha plus perlite. This is the region, so that is austenite. So austenite is, that is gamma. Then this is the region where what we call as austenite plus lead burite. This is the region that is from this percentage of carbon content to 4.3% at a temperature above 727 degrees centigrade, it will be austenite plus lead birote. Then from 4.3% to 6.67%. So at a temperature 727 to 1147 degrees centigrade, it is cementite plus lead birote. Similarly, coming down, so this is the region that is 725 degree, that is where it will be in solid state. So in solid state, it changes into other different forms in solid state, that is alpha plus perlite, then perlite plus cementite, once again up to this carbon content at a temperature below 727 degrees centigrade. So then perlite plus cementite. So then this region, this horizontal line, you can see, observe the horizontal line, that is the point where austenite changes to perlite. So up to this point it will be austenite. So austenite plus lead birote. So this is austenite in liquid state, it will be in liquid state. So that is austenite is nothing but that is gamma, it is represented as gamma, so gamma iron. So liquid, it will be in still liquid state. So then it will be further, it will be changing into one more relative form, that is austenite plus lead birote. So percentage of austenite goes on decreases, whereas percentage of other form goes on increases, that is austenite plus lead birote. Similarly here in this region above 4%, 4.3% up to 6.6%, it will be, as I told in the beginning, it will be, that is Fe3. Fe3 is nothing but cementite form of iron. So this is cementite plus lead birote, and below 727 degrees centigrade. So once again it will be cementite plus lead birote. So here in this region you can observe from 2.7 to 4 up to 4.3%. So here austenite, the austenite gets changed into one more form, that is perlite. So lead birote, it will be as it is. So austenite which was there above 727, it gets converted into perlite. So perlite plus lead birote. Similarly here it is gamma plus cementite. So below which, so once again cementite gets converted, changed into perlite plus cementite. So here it is alpha plus perlite. So this is the vertical line is the perlite. So this pure perlite, this is perlite plus cementite, and this is perlite plus Fe3C is nothing but cementite. So these are the different points what we can study from the, that is iron carbon diagram. So this is the point, that is it contains 0.53% of carbon content. So peritectic point, then eutectic point, eutectoid point. So you can observe here. So what are the observations you can make is that E is the eutectic point. So this is the eutectic point. So what is eutectic, what is eutectoid, what is the peritectic, all these things already it has been discussed in the phase diagram. So continuing that, I am representing these different forms. E, this is the point, that is eutectic point, E gamma, so that is called as eutectoid point. Then this is the delta, that is alpha austenite. So alpha austenite, this is alpha. Then this is delta, and then this is, that is gamma austenite, ferrite and delta. So as I told, A, B, E, C is the liquidus line, and PP is the peritectic point, this is called as peritectic point. So these are the observations or what we can study from the iron carbon diagram. Now once we draw this iron carbon diagram, so one more thing that has to be studied is nothing but what are the different phases that can exist in case of iron carbon diagram. So what are the different phases? So coming to that point, so iron carbon diagram can exist in, that is 5 different phases that exist in case of iron carbon diagram. So what are those phases? So what are those phases? The first one is alpha, then gamma, delta, alpha ferrite. So alpha ferrite, so you can see, observe here, so that is alpha. So this is alpha, this region that is from 0 to 0.08% of carbon content, and up to this that is percentage up to a temperature of 912, this region is called as alpha ferrite. That is one of the phases of iron in case of iron carbon diagram. Now this alpha ferrite will have a BCC structure. If you study that phase, the structure what we can see is the BCC structure, that is body centered structure. Now this is the softest form of iron. Ferrite is the softest form of iron. So and since it is softest, we can change into any other different shapes and sizes easily. We can change it into any required shape and size easily. So softest form of iron is, that is alpha ferrite. It will be having a BCC structure. If you study, it will be having BCC structure. So its temperature is, that is 912 degrees centigrade. Percentage of carbon content is 0.08% of carbon content. That is, ferrite consists of, that is the percentage of carbon, and temperature is 912 degrees centigrade. Then the second one, so alpha, gamma, delta. So gamma austenite. So gamma austenite. So gamma austenite you can observe. So that is here, this is the gamma. So here austenite. So gamma austenite. So gamma austenite, this region. So that is the other form of, that is other phase what we can study in case of iron carbon diagram. So if you study that, it will be having FCC structure what we can see in this phase, that is FCC structure. So it is up to a temperature, so up to a percentage of 2.7% and up to a temperature of, that is 1394. So 1394. So this region is called as, that is your austenite. So that is alpha, that is gamma, delta. So gamma austenite is that region. So it will have FCC structure, and it is non-magnetic. It is non-magnetic. So one of the properties of this phase of iron is it is non-magnetic, and it is unstable at low temperature. So it is unstable. So we can make it stable. We can make it stable by rapid cooling. So by rapid cooling of this austenite, so rapid cooling of austenite, so we can make it, or we can bring it into stable state. That is the second phase what we can observe in case of iron carbon diagram. Then third one is delta ferrite. It is also called as delta iron. So delta ferrite, or it is also called as delta iron. You can see this region. That is up to a that is percentages, that is around that is 0.10% of carbon content. Then temperature in between 1394 and 1538. So this is the delta. Here it will be delta plus liquid. It will be still in liquid state. That is the third phase what we can see, that is delta ferrite. So delta ferrite, it is also called as delta iron. So other name for this phase is delta iron. Now it will be this phase what if we study, it will be magnetic in nature. So magnetic, it has got that magnetic property. That's how that is the reason why iron can have different properties at different stages. We can have different properties. That is the reason once again why we should study the iron carbon diagram. So this phase, that is delta, it is also called delta ferrite or delta iron. It is magnetic in nature. And it is stable at high temperature. So up to 1394. This is 1394. Up to that point it will be stable. So that means you can observe that it is stable up to a very high temperature. So only in applications where the temperature is higher than this temperature, that is 1394. So we cannot use this this form of iron. Then fourth one is iron carbide. So iron carbide is also called as cementite phase of iron. So here it has got low tensile strength, one of the properties. Second one, high compressive strength. So tensile strength and compressive strength, so we are discussed in the mechanical properties. So mechanical properties, what is tensile strength and what is compressive strength. So tensile is one where the material is, that is load is applied and it's pulled outward. Compress where the material load is applied and compress so that what is the strength up to it can take before failure. So it has got low tensile strength, whereas it has got high compressive strength. This iron carbide, that is the iron carbide or cementite, it is the hardest form of iron. So you can see this Fe3 is nothing but iron carbide. So up to a temperature of that 1475 with a carbon content of 6.67%. So that is iron carbide. The other name is called as cementite. Then one more form of one more phase in case of iron carbide is called as lead burette. That is nothing but here alpha we got gamma and delta. Lead burette is the combination of Fe3C. Fe3 is nothing but cementite plus alpha delta gamma, you got delta plus Fe3. So lead burette you can observe here. So this is austenite plus lead burette. So then cementite lead burette. So that is above temperature of 727. So below it is 727, it is perlite plus lead burette. So whereas in this region from 4.3 to 6.6% carbon content, it is cementite plus lead burette. So that is one more form of phase of iron, that is austenite plus cementite. So that is combination of austenite plus cementite. Then the last phase what we can see in case of iron carbon diagram is perlite. So perlite you can see this is the region that is alpha plus perlite plus cementite, that is up to a percent of carbon content, that is around 2.7%, around up to percentage of carbon content is 2.7%. So below 727 degrees centigrade, below 727 degrees centigrade, that is the perlite, that is the one more phase in case of iron carbon diagram. So these are the different phases we can observe in case of iron carbon diagram. So one more important aspect what we can study from this iron carbon diagram. So initially we had seen that what are the different components, what are the different status in which we can get that the particular type of phases that we had studied. Now one more topic what we can analyze or study from this iron carbon diagram is about invariant reactions. So what is invariant reaction? So you have studied in your Gibbs phase rule, one of the topic in the previous sessions. So where we can establish a relationship between the number of phases, components, number of phases and components. So Gibbs person who's conducted a study and he had come with a rule called as Gibbs phase rule. Now according to Gibbs phase rule, F is equal to C plus 1 minus P. So where C is the number of components and P is the number of phases. Now if the value of this F is 0, so then we call that as invariant reaction. If the value of F is 0, so then we can call that reaction as invariant reaction. Now if we study this iron carbon diagram, so we can come across three different invariant reactions. If you study the iron carbon diagram, we can come across three different invariant reactions. First one is eutectic reaction, second one is peritectic reaction, third one is eutectoid reaction. What is eutectic, what is peritectic, what is eutectoid? Already it has been discussed in the previous session, that is in types of phase diagram. Now here we can have three invariant reactions. So first one is eutectic reaction. So what is the reaction that takes place? So where liquid on cooling or heating will give austenite plus cementite, that is delta plus Fe3C. So Fe3 is nothing but the cementite. So liquid on cooling gives austenite plus cementite. Now this eutectic reaction, it takes place at temperature of 1147 degrees centigrade and 4.3% carbon content. You can observe, so 4.3% of carbon content, this is the point, and temperature is 1147. So this is the point, that is E is the eutectic point. So this point is here the transformation takes place. So here the transformation takes place, that is E. So liquid on cooling gives austenite plus cementite. So austenite plus cementite. So here up to this percent of 4.3% carbon content at a temperature of 1147, this region austenite is one form, then cementite is up to this temperature, that is the first one, that is eutectic reaction. It takes place at a temperature of 1147 degrees centigrade and carbon content is 4.3%. Now I told it is an invariant reaction. Now if we study that, number of phases are three, one is liquid phase, one is austenite phase and one is cementite phase. So during this reaction we can come across three different phases, that is P value is equal to 3. Number of components, so number of components is austenite plus cementite. What is from the reaction we can see that it is a 2-component system. It is a 2-component system. So C value is 2. Hence, if you substitute and simplify, F value you get as 3. F value you get, that is 0. F value is equal to 0. That is why we call this as a invariant reaction. Then one more second type of invariant reaction is called peritectic reaction. Peritectic reaction. So it takes place at temperature of 1495 degrees centigrade and 0.18% carbon content. You can observe this 0.81% carbon content, and then temperature is 1495 degrees centigrade. So 1495 degrees centigrade and then 0.18% carbon content. This is called as peritectic point, where we can come across this peritectic reaction. So this temperature, if you draw horizontal line, 1495 degrees centigrade at a carbon content percent of 0.18%. So that is where we come across this peritectic reaction. So what is the change, that what is how the reaction takes place? So here liquid, so you know that above it is in liquid state, above this point it is in liquid state. Liquid on plus, that is your delta gives, that is austenite. Liquid plus delta gives gamma. Liquid plus delta gives plus, that is gamma. So you can see this liquid above this, it is delta plus liquid, that is liquid plus delta. So that gives austenite. Below it, below this temperature, it is austenite. So that is the reaction. It is called as peritectic reaction. So where liquid plus delta gives either cooling or heating, we get one more form, that is austenite. It is taking place at a temperature of 1495 degrees centigrade with a carbon content of 0.18%. Then the third one is Eutectoid reaction. So Eutectoid reaction, so that is at a temperature of 727 degrees centigrade and 0.83% carbon content. So you can look at this. This is a 0.83% carbon content, temperature 727 degrees centigrade. Already we have discussed, that is E gamma is nothing but Eutectoid point. So the reaction that takes place at this point, so at this temperature, so it is eutectic temperature is 727 degrees centigrade, percentage of carbon content is 0.83%. This point is called as Eutectoid point. So the reaction what we can observe at that particular point is called as Eutectoid reaction. So Eutectoid reaction, austenite on cooling or heating on the other, either way, it gives out ferrite plus cementite, ferrite plus cementite. So austenite, so above this we can know though this is the region. So in this region above this point it is austenite. So austenite getting converted into perlite plus cementite. So that is ferrite and cementite. So here you can observe that here this is the region, that is it will be one more form ferrite and then cementite is there. So that is the third invariant reaction where austenite gets transformed into, that is ferrite and cementite. So three invariant reactions we come across. So one is eutectic reaction, second one is peritectic reaction, third one is eutectoid reaction. This is one more topic what we can analyze in with respect to this iron carbon diagram. Next, one more point we have to study is that what are the critical temperatures we can come across. So critical temperature. So what is a critical temperature? Critical temperature is the temperature at which transformation takes place. Critical temperature is the temperature at which transformation takes place. Now if we study the iron carbon diagram, we can come across three points or three critical temperatures, that is A1, A3 and AC. So you can observe here, this is A1, this point, then A3 is this point, AC is this point. So these 3 points or temperatures at these points are called as critical temperatures. So critical temperature where transformation takes place. So coming to the first one, A1. So you can observe this diagram once again. A1, it is the temperature, that is 727 degrees centigrade. 727 degrees centigrade. So that is where eutectoid transformation takes place. It is a temperature at which eutectoid transformation takes place. So that is the first critical temperature or critical point. Second one is A3. So where is A3? So A3 is here. Then AC is at this, on this curve portion. So AC is there. On this curve portion, A3 is there. So A3 is the hypo-eutectoid steel. So A3, it takes place between, if you observe, 0.08% to 0.83%. So this is the region. This is the region, 0.008% to 0.83%. So this is the region that is hypo-eutectoid steel, what we get. So hypo-eutectoid steel, that is from 0 to 0.83, but here it is from 0.008 to 0.83. So this is the transformation where it gets transformed into hypo, that is eutectoid steel. So a major transformation takes place, hypo-eutectoid steel, that is one more critical temperature, that is A, that is 3. Then next AC. So AC, this is the point, AC. So AC is once again a hyper-eutectoid steel. So where transformation takes place into hyper-eutectoid steel. So that is 0.83 to, that is up to, that is 2%. So it is 0.83 to 2%, that is in this region, 0.83 to 2%. So this is the point, a critical temperature point, where it gets transformed into hyper-eutectoid steel. So as I told in the beginning of the session, so in steel we can have two types, that is hypo-eutectoid steel and hyper-eutectoid steel. Similarly, between 2 to 6.6% carbon content, so we can have call that particular type of iron as cast iron. So where carbon content goes on increasing between 2% to, that is 6.67%. In this, once again we can have two types, that is hypo-eutectoid cast iron, hypo-eutectic cast iron. That is 2 to 4.3%, it is called as hypo-eutectic, where it is cast iron. From 4.3 to 6.67%, it is hypo-eutectic cast iron. So these are the different things we can analyze from phase diagram. So what we are discuss is how to draw a phase diagram, what are the salient features we can look at from the phase, that is iron carbon diagram. So it is where we can study the changes that takes place with the change in percentage of carbon content and temperature. So change in percentage of carbon content on x-axis, whereas temperature on y-axis. So what are the salient points we can analyze or study from the iron carbon? That is the first thing what we have discussed. Second thing we have discussed, so what are the different phases that can exist? So 5 different phases that what we can see in case of iron carbon diagram. And third topic is what is invariant reaction? What are the different types of invariant reactions we can come across in iron carbon diagram? And the last point is critical temperatures. So what are the critical temperatures we can observe in case of this iron carbon diagram? So 3 critical temperatures, so A1, A3 and C. So where transformation takes place, that particular temperature is called as, that is critical temperature. So this is about this very important topic, that is iron carbon diagram.